Hi everyone, my name is Neha Kardam, and in this lecture we are going to learn about shift registers. So these are the topics which we'll be covering in this lecture. We will learn about overview of shift registers. We will learn about the characteristics of shift registers and then serial parallel data conversion, serial load shift registers, parallel load shift registers, recirculating shift registers, and using the 74194 shift register IC. So let's start with the overview of shift registers. So shift registers, they are basically sequential logic devices which are made up of flip-flops that allows parallel or serial loading and serial or parallel outputs, as well as shifting bit by bit. So these shift registers, they have flip-flops which are connected in cascade, and they share the same clock in which the output of each flip-flop is basically connected to the input data of the next flip-flop in the chain, and they result in a circuit that shifts by one position, or you can say that they shift by bits, bit by bit. Now let's see what are the different tasks which a shift registers can do. So it can use in data conversion, serial or parallel data conversion. It can be used in UART, which stands for Universal Asynchronous Receiver Transmitter. It's basically used as a physical circuit in microcontroller or in a standalone IC, and the main purpose of this UART is to transmit and receive the serial data. And then we have time delays. It can be used in providing the time delays. So you might going to see in some microprocessor circuits where we will basically provide that time delay, and in that we will be using these shift registers. They can be used in ring counters, and they can be used in twisted ring counters. So these are the different types of counters in which shift registers can be used, and they can also be used in memory devices. Now next is characteristics of shift registers. So number of bits can be used in shift registers can be 4-bit, 8-bit, 16-bit, 32-bit, and so on. They can load data in serial or in parallel, asynchronously or synchronously. So synchronous, asynchronous, we have learned in previous lectures what are these and how they can be used. And they have like different modes of operation. So these are some common modes. They can work in parallel load, they can shift from right serial load, they can shift left serial load, they can hold the data, they can clear the data. So when I say that shift right serial load, it means it can shift the data to the right side, and shift left is loading to the left hand side. And then parallel load is like directly going into the input and then going output, going out of the output side. And then we have recirculating or non-recirculating type shift registers. So we are going to see some of these in this lecture. Now moving on to the next slide, serial parallel data conversion. So in this shift registers, they can convert the data from serial to parallel, and also they can convert from parallel to serial. So let's see an example. So this is the 8-bit binary data you see here, and this can be moved serially. So you can see this is going in serial in, and then this is coming out serial out. So if your data is moving in this way, in this direction, then in this way, then you will say that it is a serial in serial out type. And then you have serial in and parallel out. So you are sending the data in series, and then you are taking the data in a parallel form. So directly your output is connected and you are taking the data in this form, and you are feeding the data in this form. So for example, if you are feeding just 1 and then 1 goes, or maybe 0 goes in here, then 1 moves to there, and then so on, and then that whole, every time the whatever the change is basically reflected on this 8-bit is basically comes out in a parallel form to this side. And then we have parallel in and serial out. So your input is sent in a parallel form. So parallelly you change all these 8 bits, and then you take the output serially one by one from here. And then this is another type in which you input the data in a parallelly. You directly just feed some input into this 8-bit, and then you take out the output, whatever the change, the new 8-bit data comes out to be is directly taken out from the this type of shift register. So these type of data conversion shift register registers they can do. Now let's see some quiz question. So this represents a dash register. It is whether it is parallel in, parallel out, or it is serial in, parallel out. So what do you think? So we are sending this data 10 into this 8-bit register, and then data is coming out in this way. So certainly we know that data is being sent serially in, so it is a serial in, and the data is coming out in a parallel form. So this is going to be serial in and parallel out, and that's our answer is. Now next question is what does this represent? Is it a parallel in, parallel out, or serial in, serial out? So it's pretty easy. You see that data is going into this 8-bit register, and then shifting the data, and the data is coming out from this side, which is serial out. So if the data is basically transferring in this form, then this is called your serial in and serial out. So this is serial in, serial out. And then if you have the data going in this form, so this is, you know that this is parallel in, and the data is coming out from here. So you see that this is a parallel in and serial out type shift register. So parallel in, serial out. And next we have data is going in the form of parallel and then coming out in the form of parallel. So this is going to be parallel in and parallel out. So B is the right answer. Parallel in, parallel out. Now next is we have serial load shift register. So this is our shift register circuit when the data is loaded in the serial form. So you see that the main key feature is here is that the clock is connected to all the flip-flops. So this was not present in the counter. So here this is the difference from the counter circuit, is that the clock is present, is connected to each flip-flop, and all the clears are tied up together, and then data input is going into this flip-flop. So in this particular case we are using D flip-flop. So you see D is the input going in, and all of these are D flip-flop, and then output is sticking out from this Q. So these are our output. Now let's see. Note that the use of D flip-flops, clock inputs wired in parallel. So that's what we see here. They're wired up in parallel, and clear input can be activated with low. So when your provide 0 to the clear, that means it will be activated, and when the clear is 1, then clear is disabled, and preset inputs are deactivated. Now these are the parallel outputs here, A, B, C, D, and these are the inputs here, data, clock, and clear. Now let's say clear input. So it tells like if it is 0, then it is activated. If it is 1, then this clear is deactivated. Now clock input, here we are giving the positive edge triggering. So at the positive edge, at the positive edge, the circuit will trigger. So every time you have like positive edge going into the flip-flop, then these all flip-flop will be basically turned on. So in this particular case, when the data is 1, your data is going 1 into the D flip-flop, and your clock pulse is 1 here, it is a positive triggered, so it should trigger at this point. But however, if you see here, the clear is 0. So if your clear is 0, it means the clear is activated. If your clear is activated, then your output you're going to get is all zeros. So to get some output here, we need to deactivate the clear. So let's see next. In this case, when the clock pulse 2 is provided, at that point your clear is 1. So clear is deactivated. At this point, whatever you send data at D flip-flop, it will go out on the output. You know that in D flip-flop, whatever you provide at the input, that basically shows at the output. So if your D is equals to 1, then the Q is going to be 1. If your D is 0, then Q is going to be 0. So in this case, we have D is equals to 1. That's why you have A as 1 over here. And then this data will send over here, and then you will see like how it changes. So in the pulse 3, data is 1, and then the previous data goes into this flip-flops, making this Q turned on to 1. And then in the third one, you see we have data is equals to 0. So previously it was 1. For last 2 stages it was 1, and now it is 0. So here you need to know that this is 0 at clock pulse 4. So circuit is activated, but then if you send 0 data here, then you're going to get 0 over here. That's why you see 0 here. And then these two flip-flops, they are still taking the old value from the flip-flop, because this is the new data which has come up, and this hasn't yet reached to the flip-flop. So this is responding to the previous value, which was 1 over here, and that's why these two are turned on. And you see here 0 1 1 0, and then again if you send the 0, then what will happen, that 0 will go into this flip-flop, making this 0, and this will remain, this will again going to be 0 because the data we are sending is 0. And then you see that this will still respond to what was the previous input going into this flip-flop. That's why you have this 1 here. And then the input to the fourth flip-flop is 1, so that's why you got at the output as 1. So if you notice from the previous previous slide that how the data is moving. So previously you have 0 1 1 0, and now you have 0 0 1 1. And when we go further, if you keep sending the 0 data, then you see that how the 1 is changing, is basically shifting to the right. Okay, so we saw that previously it has 1 here which has moved over here, and this 1 has moved to out. So now you have a 0 0 0 1. Now if you again provide 1 to the data, then what will happen, your D will become 1 and you will have this output. And if you keep providing, if your next pulse is 0, data input is 0, then what will happen, your D will become 0, and this 1, the one which you have provided previously, will move here. And if you keep on providing data is equals to 0, then what will happen, this is going to move here and then further here, and then it will be out. So this is your 4-bit serial in and parallel out shift register. So you see that you are serially giving the input to the flip-flop and you're getting the output in a parallel form. And if you want to get the output in a serial form, then you can just like stick out the output from here. Now let's see some quiz questions. So the first question says, this is what type of shift register? So if we look at this picture, then we see that the data is coming in serially and going out parallelly. So this is the serial in, parallel out type shift register, and it is similar to the circuit which we saw in the previous slide. So this is serial in, parallel out. And then you have what is the 4-bit output, bit A on left and D on right after one pulse. So this is bit A on left and D on right. So okay, so at one pulse, when you have clear is equals to 0, so you have to look all these three inputs. So this was a little tricky question if you ignore this clear 0. So this is active low clear. So if you have 0 here, which means that you are going to get the output as 0. So the output is going to be 0 0 0 0. So circuit is not yet activated because clear is activated right now. And then you have what is the 4-bit output in this case when the pulse 2 is provided. So in this particular case, if you notice that your clear is equals to 1. So whatever data you send here is going to transfer into here. So if you're sending 1, then the output is going to be here 1. And I'm assuming that previously we had like 0 0 0 0. So if we after that, if we provide this data 1, then this is going to be 1 0 0 0. And this is clear from this clock pulse also. This is the second clock pulse, and previously it was the first clock pulse. So the output is going to be 1 0 0 0. And let's see in the third clock pulse when your data is 0 and this clear is 1. So in this particular case, your output is going to be 0, and whatever the input was previously you had here will go into this flip-flop, making this as 1. So you're going to get 0 1 0 0, and that's your answer. And then another for another clock pulse applied, clock pulse 4, and data is 0. And then what will happen? So now the input or the output of this will go into this register, and you will have 0 0 1 0, because here you have data 0, so this is going to be 0, and previously it had 0, your A was 0, so which goes into this flip-flop, making this also as 0. So you will have 0 0 1 0 as your answer. And then finally, what will happen in the clock pulse 5? So here you gotta notice this thing that we have data is equals to 1. So previously it was 0, now you are sending 1, so this is going to be 1 here, okay? And then these are going to be zeros, and then this guy, this D, is going to be 1 because the the input going into was 1. C was 1 previously, so this is going to be 1 0 0 1. Okay, now in this one, what's going to happen? So in this clock 6, when your data is 1, so previously it was 1, so this will go into this D flip-flop, this will turn on this as 1, and now you have this new 1 going in. So these two are going to be 1s, and these two are going to be 0s. So that's why you have 1 1 0 0. So these were all the quiz questions. Now let's move on to the next topic, which is the parallel load shift register. Now this circuit is different than the previous circuit which we saw. In this one we are using the JK flip-flop, and if you notice that clock is in this one is also tied up, and you can see it is connected. The clock is connected to all the flip-flops, and then you have all the clears. These are connected to this this clear, single clear. And then you have all these preset going out from here, connected here, and then your output is coming out from this Q. You see here, this Q is basically shows your output. And then there's one different thing which you may notice, that you have this Q bar is connected to this K, and then this Q is connected to this J. Okay, so it is kind of forming a ring. So whatever your output is will go into this J, and whatever your output you get at Q dash or Q bar, that will go into this K input. So note the use of JK flip-flops, clock input wired in parallel, so we already know that, and clear input activated with low. So clear will be activated when you give 0 and deactivated when you give 1. Parallel load input ABCD are active low. So parallel load inputs, these are active low. Now note the recirculating lines. So we already noticed that how the output was going in as a basically fed as a input to the JK flip-flop. So recirculating lines basically pass the data from flip-flop D. So this is D flip-flop, A, B, C, D, from D to A flip-flop on each clock pulse. So every time the clock pulse hits up, this D flip-flop will basically transfer the data to the A flip-flop. And your outputs are coming from here. So these are your output here. So parallel data input, which is active low, works for active low, is basically sent through these preset. When these are sent through here, then what will happen? The next step we have to watch is the clock. So in this case, the clock is going from high to low. And then we have clear input, active low. So you will send the data input through these. So it's the same thing. Now we will see that the function of that loaded shift register as a recirculating shift register. So we'll see that here. So parallel data inputs, in this particular case, only deactivated. D is activated here. But if you notice, these are the three inputs. If you notice here, we have clock pulse 1. But if you notice to the clear, it is equals to 0. Which means whatever you send over here, it's going to give the output 0 because the clear is activated at this point. And clear is our active low type of input. Now in this one, if you see that clear input is 1, so it means it is deactivated. So whatever you send here, we are going to get some output for that input over here. So parallel data input is sent as C and D as activated. So you see C and D, these two are activated. These are sent here, and these A and B are zeros. And so what will happen? So whatever your output is in this case will basically go into the J and K flip-flop, and from here, and then based on the input received, it will basically show your output. So that's why you see here A and B are not active, or they are showing as low, and only C and D are activated, and that's why you see here 0011. Now let's see the second state. When all the inputs are parallel data inputs are inactive, which means you are giving 0000. In that case, what will happen? So in that case, this is going to be your output first of all, and we will see how we got this output. So to understand how we got this output, we need to know what was the previous output sitting here. So I'm going to go back. I'm going to go back to the previous slide. So this was our output previously 0011, which means here at the output you had 1, and here at the output you had 1. So what will happen if your Q for this D flip-flop, your Q is 1, then Q bar is definitely going to be opposite because it basically toggles. So if this is 1, then this is going to be 0. So this one will basically goes to this A flip-flop, and into this J term, J input, it will go in here. So at J, so this J will be equal to 1, and then this 0 which is coming out from this Q bar will basically goes into this K input. Okay, so which means your J is equals to 1 and K is equals to 0 for this particular flip-flop. Okay, and then if you see that this Q, which is 1, is going into this J, and Q bar is opposite of Q, so which is this is going to be 0, so 0 going into this K flip-flop, not the K flip-flop, to the K terminal. So for this D flip-flop, J is equals to 1 and K is equals to 0. Now if you recall your JK flip-flop truth table, and in that when J is equals to 1 and K is equals to 0, in that case your output Q is going to be 1. So if you verify that and then come back to this circuit, you will know that what output you are going to get. So when J is 1, K is 0, then in that case your this Q is going to be 1. So you're going to get 1 over here, and you're going to get 1 over here. So in this particular case, when all the inputs are inactivated, when you have all 0 0 zeros here, then the output which will be generated based on the input you have here. Okay, so that's the reason why you are seeing 1 here, because of the input which is coming out from this D flip-flop and going into this A flip-flop. And that's why you see 1 here and then 0 0, and then you see 1 here because previously it has 1 here. So based on that JK input, you got here output as 1. Now in the next stage, when you have pulse 4, clock pulse 4 and parallel data inputs all are inactive, and in that case then what will happen, your output from Q will get into this flip-flop, and that will make this Q output as 1. That's why you see 1 here, and then this Q will remain at 1. The reason why, because the previous output which was here was 1 here, and that's why you got 1 here. And then let's see next. So you will get 1 1 0 0. This will change to 0 because now the next input which it got, this D flip-flop got, was 0. So if this is 0, J is 0, then K is going to be 1 because Q bar is opposite of Q. So for this case, when you get this, at that point your J is basically 0 and K is 1, and when you have J 0 and K 1, then your Q is going to be 0. Okay, now let's see in the next pulse, which is pulse 5. So if we see from the previous output which we got, Q was 0 and Q bar was 1. So this 1 will go into this K flip-flop, A flip-flop. So K is 0 and K is 1 and J is 0. Because Q was 0, so 0 goes into the J and 1 goes into the K. So when J is 0 and K is 1, then the output is going to be 0. And that's why for this clock pulse you see here 0. And then whatever was input previously you had will go into this flip-flop, and same with this flip-flop. And that's why you see here 0 1 1 0. And then in the sixth pulse, what will happen, that 1 1 will move to this C and D, because the output of the one flip-flop will behave as an input to the another flip-flop, and then based on the input received, the output will respond. So based on the input condition, we got 0 0 1 1 at clock pulse 6 when all the inputs are inactivated. And at the 7th pulse, what will happen? At the 7th pulse, everything is 0 0 0. So all of these ABCD, they are given with binary 0000. The reason why, because if you look at here at the clear input is equals to 0, so your clear input is activated, your CLR is activated. When that happens, then you will have all zeros here, and if it was 1, then the situation could have been different. You might have like the last one could have gone here. Now let's see next. Parallel data input only be activated and clear input 1. So it is a activated condition. Your clear input is 1, so it is clear input is basically deactivated, and your in parallel input you're giving 0 1 0 0, so 1 is going in here. Okay, so if you have something like that, then what will happen? Based on the previous input received, this output will respond. So so based on that, you have 0 1 0 0. Now let's move on to the quiz. After clock pulse 1, the output from the shift register will be so it is active active low clear. So clear input is equals to 0, so whatever you give, it doesn't matter. You will always have 0 0 0 0 here. After clock pulse 2, the output from the shift register will be, so now here clear input is 1, clock pulse is 2, and B and C are activated. So B and C are activated. In that case, you will directly get B and C as 1 over here. So that's why you got 0 1 1 0. And then third clock pulse, when none of the inputs are activated and clear input is 1, then what will happen? Then this is going to move this that's what's the function of the shift register, is to move the bit. So these bits will move. So now you're going to get 0 0 1 1. So that's your answer. And then after clock pulse 4, the output is going to shift to more. So this is going to become 0. So 0 1 0 0 1, and then this 1 which you have here goes into this here, J and K. J will be 1 and K will be 0, and it will produce 1 over here. So you're actually going to get, in for this particular case, as 1 0 0 1, and that's your answer. At clock pulse 5, all the inputs are inactive. Now what you're going to get, so this one is again will go into here, and then this output will get into this flip-flop. So which means at the output of this flip-flop you're going to get 1, and the output of this flip-flop also you're going to get 1, and rest of them are going to be 0. That's why you have 1 1 0 0 answer. At clock pulse 6, all the conditions are same. What you're going to get, so this bit is going to move. So this 0 will go in here, making this J is equals to 0, K is equals to 1. So this output is going to turn to 0 now. And then whatever the input was previously goes into here, and then it will produce 1 here and then 1 here. So this bit basically it will move to here. So this will become 0 1 1 0. And that's your answer. So these were the few questions in this for this particular topic. I hope you understand. Now let's move on to next topic, which is universal shift register IC. So in this universal resistor, it is so this IC which you see here, it is 74194 4-bit shift register IC, and it can work on different modes. So you see that when so this is clock and this is S0 and S1. So when your S0 and S1 is equals to 1, then that is called your parallel load operation. And when your S0 is equals to 1 and S1 is equals to 0, that is called your serial shift right. So this is called your shift right, and when they both are 0, then that will be your hold position. And when When S0 is 0 and S1 is 1, then that is called your shift left. Here this clear, you see here, it is active low input you are giving into this IC, and serial R inputs, serial L input, and these are the output binary output you get from here. 5 volts is the supply given into this IC. So let's read here 74194 is universal 4-bit shift register IC. These are the different modes of operation we have already discussed. And active low clear, we already know it. These are the outputs. These are the different modes which can be controlled from here. Depending upon what input you send here, you will get corresponding to that particular mode. Clock is going from low to high, triggering, and then parallel data input, you are sending it from here. And the order is A, B, C, D. If you see here, this is A, B, C, D. This is clear input active low. And this is serial data write input, which is used during serial load write mode of operation. And then this one is used during left mode of operation. Now using the 74194 shift register IC, so clear is 1 right now, which means it is deactivated, and serial R, this R is equals to X. X is like irrelevant, whatever you give, either 0 and 1, doesn't matter. Parallel load you're giving to the A, B, C, D is 0, 1, 1, 0. Serial L is equals to X. It is also irrelevant. And then clock pulse is 1. It's going low to high, and so that, and at that time your clock pulse is 1. You're giving S0 and S1 is equals to 1. So when you give both of them 1, then what will happen? The data is going to go in a parallel load. So if you see here, this is the mode of control. So parallel load when both are 1, and that's why this is parallel load. You see here 0, 1, 1, 0. So you are loading parallel data parallelly, and at the output you are getting the same 0, 1, 1, 0. Now what will happen when your serial R is equals to 0 and you have this data 0, 1, 1, 0 going in, and serial L is equals to X, and clock pulse is 2 going L to high. So in this case your S0 and S1, they are different. S0 is equals to 1 and S0 is equals to 1 and S1 is equals to 0. So that is your SR operation, shift right operation. So S0 is equals to 1 and S1 is equals to 0. So shift right, and that's why you see here serial R is equals to 0. Okay, so you have 0 here, which means shift right is activated. So when shift right is activated, then whatever you had previously over here, so previously you had 0, 1, 1, 0 here, and when this you have this in mode going in, then it will shift the data to the right. Now next pulse we have clock pulse 3. So when clock pulse 3 is sent and a parallel load is 0, 1, 0, 0, then an R is equals to 0, which is active low, and your S0 is equals to 1 and S1 is equals to 0. So still it is a shift right mode. So whatever output you have, it is going to shift. Okay, so I think I'll have to move back to the previous one. So it had 0, 0, 1, 1. So now when you have clock pulse 3, the data will move to the right. So that's why you have 0, 0, 0, 1 here. Now let's see next. In the next one, you have clear 1, serial R is equals to 0, and you have parallel load here, and then S0 is equals to 0 and S1 is equals to 0. So when both are zeros, then what will happen? That mode of operation will change. So in that case, the mode of operation is going to be hold. So you see here, it is going to hold when both are 0. So when both are 0, then whatever the output you have, it is going to hold that value. Okay, so it can basically use here as a memory, this type of shift register. So you see the application here as a memory, saving the data, whatever was the previous data, it will be stored. Now let's see next. So now here you got output data as 0 0 0. So all these fours are 0. The reason why, because if you see here, clear is equals to 0, which means it is active low, clear. So if you send clear is equals to 0, then whatever you had previously, everything will be changed to zeros. Okay, so it doesn't matter what you have here, if it is S0 is 1 or if these both are 1, doesn't matter. It is not going to send that data over here because clear is 0. So clear is activated in this case, and you have got ABCD as 0 0 0 0. Now in second case, when clear is deactivated, which means it is 1, then serial R is equals to X, irrelevant, and you have parallel load 0 1 0 0. Serial L is also X, clock pulse is 6, S0, S1, they both are 1. When they both are 1, it means it is a parallel load. So you have 0 1 0 0 going in, so that's what is going to show over here. So you have 1 0 1 0 0. Now next we have clear is equals to 1, serial R is equals to X, parallel load. So X is irrelevant, you have not connected anything. Parallel load is 0 1 0 0. Serial L is equals to 1. So now here we have an interesting case. And S0 is equals to 1 and S1 is equals to 1. So this is a shift left case and clock pulse is 7. And if you see, look here, you have serial L is equals to 1. So when you have serial L is equals to 1, so which means you are feeding 1 to the left every time your bits move. Okay, and we are going to see that. So if you remember, like previously, I'll just quickly go back to the previous clock pulse. When the clock pulse was 6, your data, which is here at the binary output here, was 0 1 0 0. Now if your serial L is going to be 1, then what will happen? You are sending 1 from the left here, and the bits are moving towards the left, which means this one should move towards here, and then this new which is 1 coming from the left side. So let's see, when you have L1, you see that that one moved over here and then new one came from here. The reason why, because serial L is equals to 1. And if your serial L is equals to 0, so which is in this case, then what will happen? You will feed 0 from here. Okay, so you had 1 0 0 1 here in your previous state. I'll just quickly go back. So 1 0 0 1. So now what will happen when your L is going to be 0, then this is going to go out, shift towards left. 0 will come here, this 0 will come here, this 1 will come here, and then if L is 0, then 0 will be fed here to the left. Okay, and that's why you see you have 0 1 0 0 for the case when your L is equals to 0. 0 0 1 0 for serial L is equals to 0. So the same thing is applied here also. If your serial R is equals to 1, then it will feed the 1 towards the right. So that case we haven't considered in this one. You can but apply it. It is the same for both of them. If you send zeros, then they will feed zeros. If you send 1, they will feed 1, either from right or left depending upon which one you are using. So this was using the 74194 shift register IC. Now we're going to see some quick quiz questions. So the 74194 IC could be described as a 4-bit shift right universal shift registers. So it is a universal shift register because we already saw that it can shift right towards left also, and it can send parallel data also. So this is a universal shift register. Now this particular case is given when clear is 0, a serial R is equals to X, which is irrelevant, parallel load is 0, 1, 1, 0, 1, 0, 0, serial R, L is X, clock pulse 1, S0, S1, both are 1. When they both are 1, which means it is going to parallelly load the data. But you need to see here, this clear is equals to 0, it's not 1. It could have loaded the data if clear was 1, which means it was deactivated, but right now our clear is activated, so this is all going to be 0, 0, 0, 0. So that's your answer. When clear is 1 and serial R is equals to 0, this is your parallel loaded data. Serial L is equals to X, clock pulse is 2, S0, S1, they both are 1. So when they both are 1, then what is going to happen? This is the parallel load operation. So no matter what you send here, your parallel load is going to be fed into the to the output. So you are going to get 0, 1, 0, 0 at the output. So this is the parallel mode operation. What is the mode of operation during and the output of the shift register after pulse 3? So at pulse 3, so previously remember we had a 0, 1, 0, 0. Now we have clear 1, serial R is equals to 0, parallel load, serial L is equals to X, clock pulse is 3, S0 is equals to 1, and S1 is equals to 0. So which means this is a shift right mode, shift right mode, this one mode. So what is going to happen? So previously we had 0, 1, 0, 0. So 1 is going to move towards right, and since you are feeding 0, so you are going to have here 0. So 0, 0, 1, 0 is going to be your answer. Now quickly see this one, when what is the mode of operation? In this case, S0, S1, 0, 0. Both are 0, then it is going to hold the data. Okay, so serial R is equal to 1, S serial L is equal to X, clock pulse is 4, clear is 1, which means it is deactivated, and this is the hold mode of operation. So whatever your data was present at these output previously, it's going to hold that. So previously we had 0, 0, 1, 1, 0, 0, 1, 0. So in this one, this is going to hold the data at the same, hold the data, and you will get 0, 0, 1, 0. Now the next one, clear 1, serial R, X, parallel load, serial L1, clock pulse 5, S0 is equals to 0 and S1 is equals to 1, which means shift towards the left. Okay, and you are feeding serial L is equals to 1, so which means from left you are going to get 1. So let's see, previously we had 0, 0, 1, 0. So now considering that the case where serial we are shifting towards left and we are feeding 1, so we are going to get in that case 0, 1, 1, 0, 1, 1, 0. So we should get let's move on to this one. So this one will move towards here, so this 0 will go here, so 0, 1, 0, and then 1 is feeding here, it's going to be 1, so we will get here 0, 1, 0, 1. So that's what your answer is, 0, 1, 0, 1. And the next one, when you have clear 1, a serial R is equal to X, parallel load, a serial L is equal to 1, clock pulse is 6, S0 is equal to 0, S1 is equal to 1. So this is again the same mode of operation, shifting towards left. So again, if you shift towards left, previously you had 0, 1, 0, 1. So previously you had 0, 1, 0, 1. So everything is going to move towards the left. So now you're going to get 1, 0, 1, 1. So at this point, if you have any confusion, then I would request you to pause the video and then do the calculation based on the inputs you have here and see if your answer matches with mine. So my answer is 1011, and this is the shift left operation. So this is the end of the video. Thank you so much for watching.